Hello, this is Rukia. In this video, I will talk about a generalized power law model on citations. This is a joint work with my supervisors Leonid and Jochen. This page you are looking at now is the outline I will present in the following 15 minutes. Let's start from the classic power law model. In the following parts, we will simply call it PL model. The classic power law model was introduced by Rukia in 1926, which was a research introduced by Rukia, and the research is about frequencies of citations in scientific publications. The more research was developed after Rukia. The power law model is widely used in different fields and good fit to size distributions in diverse areas. For example, population of cities, forest fire size, frequencies of surnames, hits to websites, protein interaction degree, etc. In particular, the power law is also very popular in bibliometrics, infometrics, and scientometrics. There are many research use the power law. For example, citations of papers, article size in a journal, publications of authors, journal loans from a library, network of citations, etc. My research focuses on citations, so I'm going to introduce the power law model setting adapted to citations. Let J represent the number of citations. Fj is the frequencies of citations. The frequencies Fj equals to C over J to the power of A, where J is equal to or larger than 0, and the constant C is 1 over zeta A. When we fit a power law model in practice, in most situations, we consider that the power law model can only describe the tail of citations. In other words, we have to add a truncation point J star, then the power law model can describe the citations larger than J star. One commonly used approach to fit the power law is to look at the complementary cumulative frequencies, which is given here. Using the slope of its log-log plot, we can find the estimation of parameter A in the power law. And there is a package in R to help us to find the A and J star. And we also notice that the power law has a skew-free property. To avoid using J star and having the skew-free property, we introduced a new model in the paper. We call it Generalized Power Law Model, or GPL model. Our aim is to use a simple model to describe typical authors' citation of their paper. There are two hyperparameters, M and N in GPL model, represents the average of number of papers and citations of an author. Then the citation frequencies Fj is given by C over J times M to the power of minus B plus 1 then to the power of A, where J starts from 0, and A and B are shape parameters here. From the following two formulas, we can see that when J is small, Fj is approximately a constant. When J is large, Fj shows the power law tail. So one advantage of this GPL model is that it can describe a whole range of citations data. From normalization, we know that C is approximately M to the 1 minus B, then times A minus 1. And the parameter A and B can be easily estimated. Even we can estimate A first, then calculate B by this formula here. You might ask, how did you find the model, or why you want to avoid the skew-free property of the parallel model? Here is the answer. We can get the limit shape. First, let's look at the integer partitions of 15. 15 can be written as 1 plus 1 plus 1 plus 3 plus 4 plus 5. And the left plots with blocks, we call it Young diagram, shows this partition of 15. From the top, it is 1, 1, 1, 3, 4, 5. If we consider these are the number of citations of an author whose 6 papers have been cited 1, 1, 1, 3, 4, 5 times respectively, then we found another way to show citations, Young diagram, or we call it citation diagram. Nu j is the count of a number appears in a partition, which is similar to the citation counts per author. Nu j is approximately m times fj. The red line shows in the Young diagram is called upper boundary of the Young diagram, and the area below the upper boundary y-axis is 15. But there are many ways to write the partitions of an integer n, and the upper boundary is not unique. For comparison's convenience, we do the scaling to make sure the area below the upper boundary is 1. Then we get a new scaled upper boundary y delta x here and here, and we replace the sum with the integral, we can get the limit shape. For the GPL model, the scaling are given as a and b here on x-axis and y-axis respectively, and the limit shape is given by a minus 2 over x plus 1 to the power of a minus 1. And it is shown as a red curve in the lower left plot. Now let me show you the real application of the PL model and the GPL model on citations. In our model dataset, we have 113 authors who published papers on the Electronic Journal of Probability, and also have Google Scholar profiles. The total number of citations, capital N, and the total number of papers, capital M, are given on the slide. There are more than 40% of 0 citations. So we decide to omit these papers when we fit the models. Estimated parameters are given here. Now let's look at the below two plots. The left plot is the limit shape fit. The limit shape of the GPL model shows in solid line, and the citation diagram shows in dots. For a better comparisons, the limit shape is plotted in scaled back coordinate, and the right plot is the complementary cumulative frequencies plot. The dots are citations, and the solid line is our GPL model, and the dashed line is the parallel model. Notice that the odd layered point at the beginning represents 0 citations. From these two plots, we can see that goodness of fit of the GPL model is excellent, but the parallel only worked well after 48. Our GPL model can also tell about the H-index. The definition of the H-index is maximum number H of authors' papers. Each paper is cited at least H times. And geometrically, the H-index is the side length of the biggest square inside the citation diagram. We have given the estimation details of the H-index in the paper. We can see that the average citation of 113 authors is 17.52, and the non-truncated power law gives 6.08, and the power law with the truncation gives 6.63. We can see that the truncation point is 48, is much larger than 17. So the power law with truncation is not actually describing the part we need. The GPL model gives 20.29, which is the closest to the real H-index 17.52. Here are some conclusions. In this paper, we modeled author-based citations with our GPL model, and it fits well in the entire citation range. And we noticed that the zero citations behave differently. Also, we can find a limit shape of GPL model, which is convenient to estimate the H-index. In addition, we have tested our model on other datasets. For example, the citations of memberships of American Mathematics Society. The GPL model also worked very well. In the future, we want to compare GPL model with other approaches, test GPL on other aggregate metrics such as G-index. We also want to look at some extreme cases, for example, some highly cited authors' citations. Here are some references. You can also find them from the paper. This is my contact details. Please don't hesitate to send me an email if you have any question. Thanks for watching.